Good morning, good afternoon, or good evening, depending on where you're listening. Welcome back to AI and the Future of Work. Thanks again for making this one of the most downloaded podcasts about the future of work. If you enjoy what we do, please like, comment, and share in your favorite podcast app. And we'll keep sharing amazing conversations like the one we have planned for today. I'm your host, Dan Turchin, advisor at Insight Finder, the system of intelligence for IT operations, and CEO of PeopleRain, the AI platform for IT and HR employee service. AI models live in the cloud and make automated decisions delivered by software via apps in the form of dialogue, predictions, and recommendations. From listening to this podcast, you might believe that's where AI starts and ends. What we haven't discussed yet is hardware architectures that could expand the scope of what AI can do. For example, the future of augmented reality and virtual reality requires vast amounts of computing power, lots of bandwidth, lots of storage, and increasingly at the edge of the network. And that just can't be provided with today's devices and networks. Just maybe there's a better way. Well, today's guest believes that carbon-based human brains can be replicated with silicon. If he's successful, it's not overly dramatic to say our very notion of what it means to be human could change forever. An open question for all of us, of course, is whether or not that's a good thing. But whatever you believe, it's important to prepare for that future because new AI-first chip architectures are inevitable. Gordon Wilson founded Rain Neuromorphics in 2017 to disrupt computing as we know it. Since then, he and the team graduated in the S18 Y Combinator batch and have raised venture funding from an exceptional list of investors, including Sam Altman, who's the CEO of OpenAI. Thanks to Rob May for the introduction to Gordon. And without further ado, it's my pleasure to welcome Gordon Wilson from Rain Neuromorphics to the podcast. Gordon, let's kick things off by having you share a little bit more about your background and how you got into this space.
Thank you so much, Dan. It's a pleasure to be here. I'm so glad to have the opportunity to share our story. And yeah, happy to kick off with a little bit of background on myself and how I got involved with Rain. I kind of come from a family of entrepreneurs. It was always sort of the expectation that I would strike out and do something on my own. And that was always something that I found very compelling, the idea of building a project and building an organization that could stand on its own and solve really interesting problems. And I also grew up in a family that was really defined by a love of science fiction that we all shared. We had this massive bookshelf filled with, Hugo award-winning, novels from Rendezvous with Rama to Hyperion. And that love of sci-fi was definitely something that sparked my young imagination, has, kept me motivated and inspired since then. But this project, Rain Neuromorphics, was started in the summer of 2017 when I met my co-founders, Jack Kendall, my CTO, and Juan Nino, our chief scientific advisor at the University of Florida. So I was studying math at the time, and Jack was a really interesting kind of interdisciplinary student himself, where he had studied physics and chemical engineering, was working in a materials science laboratory, but then was also independently studying neuroscience and artificial intelligence. He had also started a student organization at UF that was intended to teach to broad audiences the fundamentals of Python and machine learning. And that was through that organization that we met. We were sequential presidents of this student group. And Jack had been working on really thinking about this problem in a very interdisciplinary way. And that is really native to the way we understand the big problem around AI and computation, that you really need to tackle it and approach it from many angles simultaneously to be able to improve as much as we need to improve in order to fully realize the potential of artificial intelligence. And the bottom line issue is that AI is really expensive when you compare it to the brain. Our brain has 86 billion neurons, half a quadrillion synapses that run in a parallel fashion, fit inside of a 5-inch cube, roughly by volume, have a 20-watt power footprint. It is extraordinarily efficient, and it is still the most complex and biggest neural network that we have ever known, artificial or biological. And this combination of extraordinary scale while simultaneously achieving extraordinary efficiency has always been kind of our North Star of what we want to achieve at Rain. And Jack had developed a few core technologies at Florida, but it was basically there that we started the company. That was 4.5 years ago. The technology has evolved significantly, but at the end of the day, the guiding light for our technology, for our innovation, and for our roadmap that we're building is to recapitulate the brain in its entirety and to enable for independent autonomous machines to have all of those features of intelligence that we see in humans today.
What are the fundamental technological impediments to achieving that vision?
Yeah. So there really are kind of two technological pillars that have now formed the backbone of our roadmap. And these reflect the kind of core problems that we sought to solve. And those two technologies mirror the two technologies that enabled the deep learning revolution that began 10 years ago in 2012. And most people are familiar that these technologies enabled AI, but they don't necessarily know the whole history. But the two technologies that came together were a learning algorithm, a robust way to train neural networks. This was backpropagation. It was invented in 1985 by Jeff Hinton. And then a scaling architecture, a hardware platform that you can concatenate many of these pieces together more and more to support bigger and bigger neural networks. And that hardware architecture is the GPU, the graphics processing unit. That at first came to market in 1999. So backprop, 1985, GPUs, 99. It wasn't until 2012 that they came together. And what made 2012 so special with the AlexNet breakthrough was that they demonstrated you could take multiple GPUs, build a bigger neural network, train it on with backpropagation, and it beat the ImageNet benchmark, the computer vision benchmark at the time, by something like 11%. And since then, every single major breakthrough that we've seen in the digital AI world has utilized those two technologies together. And it's really been about just putting more and more compute, more GPUs behind it. AlphaGo, AlphaFold, GPT-3, natural language to CNNs to vision, it's all been driven by this learning algorithm and scaling architecture combination. Again, but the problem with that is it's really expensive. It's about 1 million times more expensive than for our brain to do the same types of neural computations. And so AI is limited in terms of how big we can scale it and where we can put it. So what we have done at Rain is we have built the analogous technologies for a new kind of neuromorphic physics-based platform for artificial intelligence. And the biggest way to distinguish between the neuromorphic way and the preceding digital way is digital AI are neural simulations. They don't physically exist. They are abstractions written in software that are run many layers above the hardware itself, where neuromorphic hardware, as we're building it, are neural circuits. They are physical instantiations of neurons and synapses. Everything has a physical element. And so our technologies are the learning algorithm and scaling architecture. That learning algorithm is called equilibrium propagation. So we developed with Yoshua Bengio, the Turing Prize winner, who's also one of the godfathers of deep learning, the circuits model that allowed us to translate this algorithm into the physical world. And it really is the first algorithm to robustly train end-to-end analog neural networks. So this is one of the major challenges we overcame. And then the scaling architecture, we call the NPU, or the neuromorphic processing unit. And it basically it answers the question, how do you fit a ton of neurons and a ton of synapses onto a single chip? And the answer is compacting them as closely as they can and connecting them with a sparse pattern. So a pattern that mirrors the connectivity pattern of the brain. So these are the two biggest problems that we identified. You need a scaling architecture and you need a learning algorithm, and these have formed the backbone of the technology at Rain.
So Rain is, I think, safely in the category of startup that we would refer to as a moonshot. High risk, but high reward. It's a put a man on the moon, put a person on the moon kind of an opportunity if it works. What's the most memorable reaction that you heard from a VC or maybe a prospective investor who didn't really get the science behind neuromorphic computing?
Oh man, there have been so many. And I mean, it's been really a funny journey for us because, Jack and I started this company and we were both 25 years old and, we're now 30. So not only were we coming with a very unorthodox approach to building hardware, but we were also just not the people that investors expected to be building this company. Today, I mean, we now realize that was why we could come with an unorthodox approach because we were from outside of Silicon Valley and we didn't have all of the biases of decades of Moore's Law style computing kind of baked into the way we understood hardware. But nonetheless, yeah, we've had some very interesting reactions. So, I mean, it's funny. One that was just recently. So we recently closed a Series A, and there was we had been pitching a fund that had invested in a lot of different chip companies, and they had looked at a lot of different AI accelerators, and they were clearly compelled by our technology, and they thought that the tech was really interesting, but they forgot to leave they forgot to remove us from the CC on an email that they were sending internally, and they've said some comment that was like, "This technology is so interesting. I just can't get over the fact that they only have bachelor's degrees and they've never come from a major semiconductor company." Anyway, we didn't respond directly to that, but we're just like, really, 4 years in and they still are discounting us for this reason. So anyway, that's happened a lot to us. And I mean, over the years, there have been countless different versions of this where we really are thinking pretty far into the future. And folks just don't necessarily buy it at its face. But one thing that has been extremely validating is that while there have been so many people that have dismissed us because our ideas were either too out there or we were too young, whenever people really pause, take the time to get to know our technology and take a closer look, they seem to walk away convinced. So, it's now a badge of honor we like to wear.
You alluded to some of what makes the human brain such a miracle, such an absolute miracle of biology, of chemistry, of science, of evolution. To a cynic who says you can't possibly capture the sophistication, at some point you just have to appreciate that the human brain is magic. To you and your co-founder who say, no, we can deconstruct what the brain's doing and replicate it with a combination of physical models and AI and do it in silicon. How do you defend that claim, given that it's still we're not there yet, but obviously making good progress?
I mean, as has other people have said in the past, any sufficiently complex technology or science is indistinguishable from magic. So, it's only natural that the most complex information processor, in this case, designed by millennia of evolution and all that it's capable of, seems almost impossible to recreate, in a silicon substrate. But, we are firm believers that this is it's a computer. Our brain is a computer that has evolved over a long period of time to process information and help aid evolutionary trajectory of life. But it's also, and it is something that can be understood and broken down, and kind of we can take the right clues from the brain. So we aren't necessarily trying to recreate the brain in every specific detail. And actually, this is an important point that distinguishes us from actually a lot of the neuromorphic projects that preceded our company. So there are a lot of folks who have been really focused on mimicking, say, the exact dynamic of a neuron and make sure that the exact way that a neuron spikes is almost perfectly replicated. And how do we build the analogous kind of sodium and potassium ion channels so the spike happens exactly. And this is what most of the neuromorphic world has been focused on. And we don't actually think it on that unit level, it actually matters as much. You need neurons, you need synapses, which are both used as memory and processing. But it's more about how do you, say, connect a huge number of neurons together? How do you scale a neural network to such a massive size that it can support really complex problems? And that's a clue that the brain clearly tells us, through sparsity, by not connecting everything to everything else, but by having these very well-connected patterns, so they can minimize the total number of connections, but still pack lots and lots of neurons together where there isn't information doesn't need to jump too many steps to travel. And then, of course, the other clue was how does the brain learn? What is the algorithm that allows synapses to know, do I need to become stronger or weaker as a synapse for the whole system to become smarter? And that was where this algorithm, which is also a very brain-like algorithm. In fact, the original paper was about bridging neuroscience and deep learning. This could be the algorithm that the brain is using. In any case, to get back to the core of your original question, we're not trying to mimic every piece of the brain, and it's not about copying it piece for piece. It's about taking the right clues. And I think when you combine those correct clues with decades of progress in semiconductor engineering, you can build really powerful products as we are doing. And I think you can even project a roadmap all the way to building a full brain. Whether when we build something that's artificial, will things like consciousness emerge? Will things, these things we consider so magical and ethereal and unique to human life or to biological life, will they emerge? I don't know, and I'm not sure. But I'm certain that we can build a far more efficient substrate of computation by taking the right clues from the brain.
So we have models in other AI domains like autonomous driving, where we've got a 5-stage process, and we can talk about the progression of the field based on going from, let's say, level 0, no automation, to level 5, a full autonomous driving, right? Is there a corollary in neuromorphic computing where, what are the early tasks that will indicate that we're making the right progress?
Yeah. So on our roadmap for our processors, we're starting by implementing our algorithm for fairly small models. We'll have to start small, and then we'll grow the chips and the models bigger and bigger. So the roadmap will begin with very, very efficient implementations of fairly simple types of machine learning. And that has always been kind of step one of neuromorphic engineering. Let's make it dramatically more efficient so we can put things in interesting places. So we'll start by, maybe making a simple computer vision task so efficient that it can go in an untethered device. But then as the roadmap continues, we add to that efficiency scale, and we start to approach far larger, far more complex problems. And I think the inflection points that I find the most interesting are ones where we can start to combine training and inference, complex training and inference, onto untethered devices. At what point can we take GPT-3 and a continuously learning model of GPT-3 that can adapt its language to the user that it's interacting with? When can we put that into a robot? When can we take, a complex robotic control that is also adaptive and learning from a complex environment, or adapting to the degradation of the machine's joints? When can we put that into a robot? I think those are some of the really compelling inflection points that I get excited about in autonomy. But it ends up kind of reflecting the autonomy roadmap, and unsurprisingly, many of our target early customers are folks building autonomous devices.
So I would think that even once the chips are capable of replicating some of the even rudimentary capabilities of the brain, in order for them to be successful, you use the term untethered or at the edge of the network, I would think there's a parallel set of technological challenges related to storage of data, because the learning algorithms presumably need to be collecting all the sensor data. How do you plan to address the storage limitations of an edge device?
Right. So a few different ways. For one, you don't necessarily need to store the entire model on the device for it to be able to continuously to fine tune itself and to keep learning. You can stream that, store a bit locally, and then have more data that kind of comes in one after the next. But I think the bigger and more fundamental solution to this problem is we really need to have an algorithm that can learn with fewer examples, which is, again, something that humans have already achieved. The data efficiency of human learning is extraordinary. We have single shot learning, two shot learning. We can generalize and take one lesson and apply it to a broader field of concepts. Whereas to do the same with regular deep learning today, things may take 10,000 examples thrown in our face. So we actually have a path towards more efficient learning in the neuromorphic domain as well. And this comes from exploiting natural quantities in the physical universe. So this might get a little technical, but it'll be an Easter egg for maybe some more of the engineers that are listening. But backpropagation is a first order learning algorithm where as it's learning, it's taking a step down this gradient. And every time it takes a step down the gradient, it gets a little bit better. There are second order learning algorithms where it's like sliding down the gradient. And we're nearly certain that the brain is using a second order algorithm. We'd like to put it into AI, but they're super expensive. And the reason why they're expensive is because inverse operations in GPUs are just really long and really expensive. So in the physical world, in the analog world, in the neuromorphic world, you can actually just flip voltages and currents and perform a natural inverse operation on the same piece of hardware because voltage and current are duals of each other. So much of the work that we do is about identifying these relationships in physics, in the physical world, and exploiting those so that the physics kind of does the math for us. Anyway, this we believe is a path towards far more data efficient learning, and it's something that can only be achieved when you're doing your learning in the neuromorphic domain.
So that got a little bit abstract, a little bit wonky. So let's take it down a level. So some of the early use cases, what kind of problems are you targeting solving?
Yeah, so I mean, initially we're looking at both being kind of a co-processor as part of a much larger model. So we might be plugged into a very large natural language model, but only do say pre-processing and dimensionality reduction for the first layer of that model. So that's one use case we're looking at now, where we're not tackling the entire end-to-end neural network yet, but just dramatically improving the efficiency of one piece. And then beyond that, we really are looking at a lot of problems in the robotics and autonomy space. So, we want to put simple vision, and even complex vision, but perception in these devices and these machines. And there still really isn't a good hardware platform to support, complex, multi-sensory perception in robotics. So we see that as another kind of entry point, a use case entry point for us. But we're really targeting this whole area around the heavy edge, where we don't need to go to the ultra low power devices because there are challenges there, and we don't need to go to the massively deployed data centers, but kind of in between where you have energy limitations, but you still want to have high performance on some fairly complex models. That's our sweet spot.
So we're all familiar, I'd say most of us are familiar with Elon Musk and Neuralink, and I'd say the general public perception is that chip implants in our brains is kind of creepy. Take the counterpoint. So what are some of the things that implants could be useful for, enabled by companies like Rain, that aren't creepy?
Yeah, great question. And I should say, we aren't initially targeting BCIs, but it is something that naturally, there's obviously a natural complement to a brain-computer interface and a neuromorphic chip. And I have a few friends who are building companies like Neuralink, and I think I should just give a shout out to Paradromics. I think they're doing incredible work, and Matt Engel is doing a great job there. But he will speak to a set of use cases I think are extremely compelling, and it starts with restoring people's capacity to experience the world as they as they were born, or maybe they were born without that. People that get injured, that lose a leg, that lose an eye. If we can build a brain-computer interface that then connects directly into your nervous system, we can restore vision. We can restore people's ability to walk. We could reconstruct spines and give people a new lease on life. And I think that to me, merits all of this work on its own. And of course, there are very interesting and bigger questions about the longer-term consequences in a society where that is possible. But I think, I would like to live in a world where, someone who is paralyzed has another chance to walk.
Love that example. Every couple of years, we hear about innovations for athletes, whether it's, the Paralympics or the bionic swimsuit that makes you swim faster because it's more aerodynamic, etc. And we always have to confront these kind of philosophical issues about at the point where we replace enough of a human with some form of technology, innovation, machine. At what point is a human? What is a human at the point where we're augmented by these digital or technological extensions of ourselves?
Yeah, that's a really interesting question. And I don't know if there will be an exact point or tipping point where we where we realize, oh, we're no longer human. It might be a sort of ship of Theseus kind of problem. As each piece is replaced, we slowly move down this gradient. But I don't know. I think that as long as it's the same continuous stream of consciousness, it will still be human, as that was a human consciousness that it started with. And one could have robotic arms and robotic legs and robotic eyes and silicon cochleas for their ears. But I think that that as long as it's part of that continuum that started with a human, that still is human. I think that there will be machines that might approximate, something that feels human in the future, and that will beg another interesting question of what happens when they're really passing that full Turing test. But I'm fairly bullish and excited about the possibility for human augmentation and sort of restoring people's capacity to interact with the world, because I just think it'll be able to extend longevity. It'll be able to give people better quality of life, and yeah, I think there's so much good that it brings to us that it's worth ultimately bringing society to a place where we have to ask those questions. And it may not be easy for us to tackle them altogether, but I think we'll be able to handle it.
Might the inverse ever occur, where you'd essentially build a robot and augment the robot, let's say with a cryogenically frozen cranium from a human corpse, or maybe it's very hard to get robots to do certain grasping tasks, and maybe you could affix a human arm to a robot. Is that inverse of the starting with the human and making it robotic? Could that play out as well?
I think that's less likely than the former. I mean, to take the example of the robotic arm, today robotic arms aren't as good as humans, but I think that once we have a bit of an algorithmic development and better compute to run those arms, then they will far exceed the precision and control of human. But to start from the machine and work backwards, I'm immediately brought to Bicentennial Man, Robin Williams, which was a great film. I mean, it's possible, I suppose. And, I think if we build in desires to machines that, that those machines want to look at us and be a human, that would be a very interesting world, and guaranteeing kind of perhaps, like, again, in Bicentennial Man, death as sort of this license to life. I think it's less likely, though. I think we're more likely to start human and work the other way. And I think that is one of the big goals of BCI, certainly from Elon Musk's perspective.
Where are we at with respect to battery or energy storage technology? I imagine these new chips will have massive requirements for energy. What are you and the team working on to make these energy efficient, these chips?
Yeah. So actually, one of the things that makes neuromorphic hardware, what we're building so great, is that we are dramatically reducing the power footprint compared to the equivalent hardware for digital AI. And we just recognize that you need to both speed up the processing and you need to reduce the power footprint in order to get the efficiency gains that come anywhere close to human intelligence. So the bottom line answer to this problem is that we are building a far more energy efficient substrate that is just going to use far less power, but it will still require more power than a human brain would, for the equivalent task, at least initially. So, I think there is, I know of different types of battery technologies that are on the horizon that, hopefully will intercept with us, on our roadmap, and we'll be able to help support, long-term storage, so we can have, several hundred or several thousand watt power footprint on an untethered device. But we are going to continue pushing our hardware to be as power efficient and as energy efficient as possible. So we hopefully won't require that to fully realize our roadmap.
So it may not get to the point where, a simple sensor, taking temperature of, in a building, or counting traffic, or, a kind of a dumb sensor, or a wearable, on a watch, or embedded in clothes, like that may not be the target for a chip that Rain is building, but something that has a little bit more capabilities might be close to where, with efficient power management, you could achieve in that kind of device.
Absolutely. Yeah. So, I really think there's going to be a whole ecosystem that ultimately supports the full artificial nervous system. We need, artificial eyes, so we need silicon retinas. We need artificial ears, so silicon cochleas. We need pressure sensing. We need everything to be taking that information at the edge of that system. But we also need something to be interconnect to the nerves and the brain, the hub for all the compute. We are really solving the brain problem. We are hoping to support kind of the hub, that central computing for all of this, neural information, where there are a lot of other companies that are building those silicon cochleas, those silicon retinas, ultra low power processors to go next to those sensors to even further reduce that information that has to be transmitted. And so I see them as the complement to what we're achieving, where we're really about the brain.
Gordon, we could take this conversation a million different directions, and I got to resist the urge, and maybe might have to continue this in another conversation if you wouldn't mind. But
I'd love to. Yeah,
you're not getting off the hot seat without answering one last question for me, and that's look, you're a science fiction buff. I'm a science fiction buff. Probably a lot of our listeners are. If Rain is when I should say Rain is wildly successful, what's one science fiction plot that you hope to be able to make reality using Rain technology? You go first.
Oh man, that's a great question. That's a great question. To not be overly sentimental, but plots like, I'll choose the films as they'd be most pretty common, but things like Bicentennial Man, things like the AI, artificial intelligence from Spielberg. I mean, they all have a bit of a dystopian edge, because it all comes to, robots feeling so human that we end up forming emotional bonds with them. But, I think in the long term, we will see, artificial systems and robots as, things that we care for and things that are part of our communities. And we'll still have human-centric communities, and that will be the foundation of everything that we build. But I would like to see those types of plots at least possible. I would like to see it possible to build machines that can interact with the world, understand the world, and empathize with humans. If that sounds a little bit eerie, and I think probably will be scary for maybe some folks, but I think that it would be a better world when we can reach that.
I want to dig up Isaac Asimov and ask him what he thinks. We might have to settle for Steven Spielberg. Maybe when you come back on the show, we'll invite Steven Spielberg as well and get his perspective.
Great. Perfect.
Good stuff. Hey, Gordon, we stuck to none of the script, and I think we had a better conversation as a result. This is a lot of fun, and I'm going to insist that you come back and have another version of this later. Would that be all right?
Yeah, no, absolutely. And sorry for getting into more wonky stuff with the technical things. I can go in a lot of different directions and levels of abstraction, but hopefully there's enough here for you to work with to make something good.
Just brilliant. Hey, if our listeners want to learn more about Rain and about neuromorphic computing, where would you point them?
To our website. So www.rain.ai. Rain.ai.
Fantastic. All right. Again, thanks to Rob May for the introduction to Gordon. This is a fascinating conversation. And this is your host, Dan Turchin of AI and the Future of Work, signing off for this week. But we're back next week with another fascinating guest.